We'll be moving to Santa Barbara. We'll be a professor here at Santa Barbara working jointly with Google AI. So it's a great pleasure. We welcome him today. He's going to tell us about synthetic atoms and an introduction to quantum mechanics and synthetic atoms. Thank you very much, Michel.
Okay. Thank you. Thank you, Chris, for this introduction. I would like to explain what will be the subject of my talk. So I intended to present you the sort of an overview of what I've been doing in my group at Yale University in the last, let's say, 2 decades. But I'm not going to enter in any, I'm not going to present you any I think, novel, strictly novel results. I wanted to, I have prepared this talk to give you a sort of introduction to what we are interested in and what we are trying to accomplish. And I think that the way to describe what we are doing, and let's see if this is going to work. Seems to have frozen up. Okay. Well, the main interest, what we are really after in our work at Yale is really quantum information physics. So it's the physics of information, and we are interested in basic questions like what are the ultimate limit of computation? How can we use quantum entities to compute, and what are the limitations in this kind of system? And our favorite atoms are superconducting synthetic atoms. And I would like to actually tell you, explain their principle and what we are trying to achieve. This is also an introduction to the panel after this talk on the possible link between quantum information systems and quantum materials. I'm not, of course, doing this alone. This is a picture of my team, and this picture can also tell you that New Haven is near the sea. It's not obvious to people who visit. They can stay 6 months at Yale without realizing that the sea is close by. Okay, so there are basically 3 parts in this talk, but I don't need to cover everything. Please interrupt me if there is a point that you would like to have more explanations on. So I will begin by telling you about this quantum microwave circuits that we're using. And Pierce mentioned the transmon, and there's also a competitor to the transmon, the fluxonium synthetic atom. And I'll tell you about these 2 varieties of superconducting atoms. And then, if time permits, I will tell you about quantum error correction, which I feel is really the heart of the problem of computing with quantum systems. Quantum systems, unlike classical systems, are very susceptible to dissipation in the environment. So on your laptop, you have actually a very effective quantum error correction system. The transistors in your laptop are submitted to a lot of dissipation. And this dissipation acts as the main mechanism for correcting errors. In fact, this error correction mechanism in your laptop is so good that essentially the errors are coming from bugs in the operating system. So it's, you basically never experience what would be an error due, for instance, to a cosmic ray in your laptop. Most of the errors are purely coming from errors in the software. In contrast, if you want to compute with elementary entities like atoms and quantum degrees of freedom, then the environment is actually will produce a huge penalty. When the environment will couple to your system, it will act as a deterrence. It will project the classical states out of the quantum superposition. And quantum error correction is actually a whole field in itself, trying to essentially encode the quantum information so that it is not only insensitive to the effect of the environment, but actively, the system is actively taking entropy away from your system and essentially maintain it in a pure state. So there's a lot of similarity between what goes on in quantum error correction and what goes on in other fields of physics and biology. Basically, a quantum computer that undergoes error correction is an out of equilibrium system in which entropy is moved away, like, for instance, in many systems in biology. So this is what I find particularly interesting, and the work is motivated by a question that physicists like Feynman, Bennett, and Landau asked in the 80s, which at that time people were concerned about miniaturization. The question was, well, if we miniaturize electronic circuits and reduce the computing entities down to atoms, what happens? And, you know, they imagined things like this kind of cellular automaton here. So perhaps most of you know that in this kind of diagram, the lines represent essentially microscopic entities, degrees of freedom that could be actually atoms or electrons. These are the lines are the degrees of freedom, and the boxes here are operations which act on either a single atom, like this box, or on two atoms at the same time. In classical physics, you need even a more complicated box which would act on 3 degrees of freedom at the same time, but quantum mechanically you can show that you can act on 2 entities, and that is sufficient. Okay, so this is basically the question here that Charlie Bennett formulated quite nicely. So there is, from a thermodynamics point of view, there is a similarity between a computer and a thermal engine. So the thermal engine converts heat into work, and the computer converts free energy into mathematical work and waste heat. And the whole idea here is to make this conversion as efficient as possible. And of course, you may want to ask, well, what about speed? It's not necessary only to be economical in terms of energy, but you want also to operate at the fastest speed. So the question is, what does physics tell us about these questions? So that's the central theme of our work. And there is a formula here which is very tantalizing. So you may, of course, it would be interesting to have powerful theorems that would tell you what is the maximum efficiency of computation, but we have a formula for communication. So communication is somewhat similar to computation. Instead of transforming the information, you just want to transmit it to another place. And here we have a very good, interesting bound. So there's a channel capacity. The channel capacity is how many bits per second can you transmit. And there's this interesting formula here that tells you that the capacity is, if you ignore the pi over 3 here, it's proportional to the power divided by h bar, and you take the square root. You can verify that this is dimensionally correct. And the results are amazing. So with 100 microwatt, which is really basically a cell phone power, you could transmit 10 to the 15 bits per second. So from that point of view, all our computation machines have an efficiency of 10 minus 7. So I have to remember you that a car runs at about a third of the max of the theoretical efficiency. So you see, there's a difference. We compute with an efficiency which is absolutely ridiculous compared with what our thermal engines are able to achieve. So can we? One of the questions is, can we do better? Are there any questions so far?
What are the assumptions that go into this equation, Michel?
Essentially, well, this is a one-channel computation. Now, if you have many channels in parallel, there might be tricks that you could use to exploit, for instance, entanglement or things like that to increase slightly this formula. So this comes with a restriction, which is that the information runs in parallel channel and the channels do not collaborate.
Right. Okay.
Sorry, I didn't get the leap from, because that one is channel capacity, and so it just tells me about transferring data, transferring bits rather than computing bits. But then somehow you said you use this formula to tell us that we are computing with an efficient.
Yes, it's an extrapolation. I agree.
But how good it is? So the extrapolation.
Yes, it's but it is yes. This is of course suggestive. It's not the entire story, because indeed computation is a transformation of the data. It's not a communication. But I think it's a good benchmark. It is not expected. Computation is not expected to deviate fundamentally.
Certainly, it will not be faster.
Yeah. So this is a sort of. I think it's a formula that is suggestive. It's not. But this is precisely the point. We would like to have a formula that would apply strictly to a computation. Okay. So this was the situation in the 80s, and then there was this birth of the quantum computer concept, which at that time was purely advanced as a sort of. There was in this period there was essentially no implication that the quantum computer could outperform a classical computer. It would just be a very economical computer. And the questions that Feynman, Bennett, and Landau were asking was that whether it would work at all or not. This quantum computer would treat the information in minimally, and the puzzle at that time was whether the uncertainty principle would derail the computation. And the answer was essentially no. There would be no problem in computing with minimal entities like atoms or electrons. But things changed in the 90s, and then there was this algorithm for factoring numbers that was invented by Shaw. But immediately after, I think the great discovery came with the quantum error correction codes. Because if you look at this factoring algorithm by Shaw, it requires incredible precision in the various gates. So the boxes that I have showed you in this algorithm would have to be precise at the 10 minus 10, maybe 10 minus 12 level for this algorithm to work. And we don't know how to make any machines that is precise at this level. So the invention of quantum error correction code was absolutely crucial, because it was proven that now you could, at least theoretically, make a machine, a quantum machine, with imperfect parts. And thanks to error correction, you could actually compute with this imperfect machine. That you can actually correct quantum information was doubted by many people, because in classical error correction, you need to measure the bits to correct them. But in quantum mechanics, measurement is invasive and destroys the information most of the time. So how you can do quantum error correction was really absolutely an intellectual feat. And I think this is really, I would say that this is the central problem now in quantum information. It's how you implement these quantum error correction codes with the maximum efficiency. And if we have time, I will tell you some of our results in our lab on this point. But before I get to that point, I would like to introduce our systems, which in this list you see line at the bottom. So we implement quantum information using superconducting circuits, and these circuits are really macroscopic. There's a few pictures of the devices that were pioneered at the beginning, but they are even bigger now. Basically, the footprint of superconducting qubits nowadays is really more like 100 micron by 100 micron rather than 10 micron. So these are really huge objects compared with other implementations which involve optical photons, nuclear spins, ions, and so forth. You probably have heard about all these platforms. So the important thing here to remember is that we encode information in many atoms that operate in a correlated way. Okay. So, yeah. So I would like to contrast what's happening in a superconducting circuit with what happens in an atom. So this is a very crude slide, but I hope it will convey the point I want to make. So the hydrogen atom encodes the information by the state of the single electron represented in green, which orbits quantum mechanically around the nucleus, which is represented in red here. In the superconducting circuit, you have a capacitance, which these two blocks of metals here, and then they are connected by this piece of wire, this inductance L. And you can view this as a sort of gigantic atom when the electrons are condensed all in Cooper pairs. In fact, in the hydrogen atom, there is the motion of a single electron, whereas in a circuit, what moves is the center of mass of all the Cooper pairs. And in fact, this motion, if you look at it, is essentially one-dimensional. There's just a charge that flows back and forth between the two plates of a capacitor, and it goes through the inductance. But basically, you have essentially one gigantic electron that orbits, if you want. So there's this similarity. We have the advantage that this atom is only moves in one dimension, so this is even simpler than an atom. And this is the analogy. So in atomic physics, we have a unique electron. In our superconducting circuit, what moves is the whole superconducting condensate, which has a single degree of freedom. The velocity of the electron, you can think of it as the current through the inductance, and the force of the electron, its analog is the voltage on the capacitance. Okay. But of course, there's a huge difference. The difference is the scale. So there's essentially 4 orders of magnitude difference in the order of magnitude of the dipole moment. So instead of 0.1 nanometer, you have a millimeter. You have essentially a charge which is also equivalent to an electron. It may be, in certain cases, it may be this whole condensate moves as displaces a charge of maybe 2 or 3 electrons. It's not very different from the atom. What is different is the distance over which the charge moves, and so you have a much, much larger dipole moment. So this has 2 effects. One effect is that it's much easier to couple to these atoms. So there's not going to be any problem. You can read out this atom. You can basically attach wires to them and measure current flowing through them. So that's a very, very, this is from the point of view readout, it's extremely useful. It's also extremely useful when you want to couple 2 atoms. You can have a common wire going through them. But of course, it presents another challenge, which is that this gigantic atom is very well coupled to the environment. So to make it, to look unconspicuous to the environment is much harder. But, and there are, as you can see, there are interesting pros and cons. Something else I want to tell you is that I have taken so far the most simple example, which is an LC circuit, just a capacitance and an inductance. And when you do the quantum mechanics of this circuit, well, you see that you will have equidistant energy levels. And what is nice, though, is that the distance between levels is directly related through this formula here to engineerable quantity. So if you can engineer the capacitance and the inductance, you see you will be able to choose the frequency difference between levels. And let me remind you that in this kind of electrical system, the flux through the inductance and the charge on the capacitance are conjugate quantities. They play the role of position and momentum in a mechanical system. So far, things look good. We have these energy levels. We can engineer their separation. We can actually also engineer the matrix elements. But there is something interesting that you must note immediately, which is that in all these states, which are called Fock states, the wave function has these properties that the charge on the capacitance can be in a superposition of being plus and minus at the same time. For instance, if you look at these two wave functions, the wave function in the ground state and the wave function in the one state, you have a superposition of electrical variables. Okay. Now, what about damping? Damping is your enemy most of the time, but it can be your friend also. So the problem with damping, with residual dissipation, is that you have a broadening of energy levels. And in fact, the amount by which the levels are broadened is given by the quality factor of this oscillator. So for instance, if you have a quality factor of 1,000,000, if you have a little bit of residual dissipation, then it means that this first level here will have, compared to its distance with the ground state, it will have a broadening which will be essentially 1,000,000th. So, of course, the state will suffer from, in terms of purity, but the advantage of dissipation, you don't want to avoid completely dissipation because it is dissipation that allows you to return to the ground state in the first place. So if you want to start from a well-defined state, basically if you want to take entropy out of this system, at some point you're going to need dissipation. What you want to do is actually organize dissipation or transitory dissipation, but at some point you're going to need dissipation. When you do the calculation, you want to turn the dissipation off, but when it comes to the job of removing entropy and removing errors, you will need dissipation. So here, this dissipation is essentially a resistance. So this is what is presented here. If the dissipation is actually cold, like you can realize a dissipation whose temperature will be a few tens of millikelvin, you see that if the frequency of this oscillator is in the range of a few gigahertz, you will be essentially in the ground state. So this is the way reset can be achieved. Now, the nice thing about these circuits is that if you have two circuits, you can couple them either by some capacitive coupling or by some inductive coupling, where the two circuits here would share an inductance. So all of this is nice, but there is one slight problem. The problem is that you cannot manipulate information with a strictly harmonic oscillator. So this comes as a surprise to the beginners studying quantum mechanics. If you have an harmonic oscillator with these equidistant energy levels, and then you shine light on this system, you won't be able to go from the ground state to the first excited state. You simultaneously activate all these transitions, and you will be able to address only one class of state, basically the class of state which is just a displaced ground state. So there's no way you would go from, for example, from the ground state to the first excited state. So we say that we cannot really steer the quantum system to an arbitrary state if this system is linear. We need some amount of nonlinearity. So we need to change this potential from a parabola to some kind of shape where the potential flares in some way. It has to deviate from a parabola. Here I have represented the case where the potential drops down as you go up in energy. And you will have a series now of L levels which will not be equidistant. So now you can, by shining different frequencies, which are represented by these different colors, then you can go from the ground state to any state in the system by a succession of pulses at different frequencies. And here comes a very, very important first quantity that will tell you about the performance of various systems, which is this nonlinearity ratio. It's the ratio between the difference between, let's say, the first excited state to the ground state difference. So this is this first term here is the transition frequency from the ground to the first excited state. You must subtract from it the difference between the first to the second excited state, and then normalize this by one of these frequencies. What it represents is it tells you, in, for instance, the emission spectrum, what is the difference between the two emission lines compared with the absolute frequency. So you may want to maximize this nonlinearity ratio because your advantage is this distance between lines. Actually, this is not exactly correct. What you want to compare this nonlinearity ratio to the dissipation. It might be okay to have a small distance here if the lines are very sharp. In practice, the effect of the environment will broaden these lines, and what you want is to maximize this product. The product of the quality factor of the system, of this type of oscillator, times this nonlinearity ratio. So this is basically what people have tried to maximize over the last two decades, basically in this field of microwave superconducting circuit. It's this product of basically this dissipation advantage times the nonlinearity. For instance, I get often asked the question, well, do we really have to use superconducting systems? Why don't we use semiconductor systems to implement circuit? Well, semiconductor systems have even more nonlinearity than superconductors, but there have way more dissipation, way more dissipation. So, to my knowledge, if you want to implement quantum information in a macroscopic condensed matter physics system, superconductivity is going to be your best bet. Now, of course, you may choose to use individual atoms in a solid state matrix. That's a form of, in fact, atomic physics in the solid state. Okay, are there some questions so far? Yes.
Hi. So this is a very naive question. Which aspect of the physical qubit encodes the potential?
Yes. So, yes, so this is something that I'm about to discuss. Indeed, how do we shape this potential? Yes. So here comes exactly the answer. So it's you need some kind of nonlinear element, but you need a nonlinear element that will have the least possible dissipation. And well, to my knowledge, there's of course a lot of effort trying to answer this question and to perfect the answer. But after many years, we are still stuck with what is called a Josephson junction, which is this sandwich of two superconductors separated by an insulator, a tunnel barrier. And this is an amazing device. We represent it by this schematic here. So it's obviously a capacitance because you have two metallic plates on top of each other. There's a very thin oxide layer. But this oxide layer, which is 1 nanometer thick is transparent to Cooper pairs. And so Cooper pairs can pass through the insulator, but they do it in a way that provides a nonlinear inductor. So this cross, of course, is a tricky symbol because it doesn't evoke an inductance at all. But the motion of Cooper pairs through this insulating barrier is very similar to an electric current flowing through an inductance. So here there's a little comparison. So you have this current that flows through this Josephson element. It's represented by a cross for historical reasons. It's just that when Josephson junctions were invented, many people realized them with a point on the surface, and so this you can look at it as two arrows touching each other. So it just evokes the way it was built originally. But this inductance behaves in the following way. So you have a current going through it, and you have a flux across it. Now, a flux here is, this is called the generalized flux. It's the inductance of the voltage across the element. It's, as you can see, it has the dimension of a flux. And if I plot the current as a function of this flux, at the beginning, you have a slope here. So an inductance would have a slope that would continue forever. This is this dashed line. But the Josephson junction has a current that goes through a maximum as a function of flux, and then it oscillates. So this is, in some sense, it is a maximal nonlinearity because if you go to very large flux, and if you average over these very large fluxes, there's no current. So if you have a very small flux, then the current will be flowing exactly as if you had an inductance. But if you increase this flux, then the element functions a bit like a switch. Rather than this current, we prefer to represent the potential. If you integrate this current with respect to flux, you will have a potential energy. And so you see, instead of a parabola, you have a cosine function. So this is called the Josephson potential. So you see, we can use this potential to create these unequally spaced energy levels. That's what we use. And so in the end, you see that when we create a circuit, it's a bit like a Lego set game. We have three basic elements. We have capacitance, essentially in the form of metallic plates that interact with each other. We have wires that form regular linear inductance, and then we have these Josephson tunnel elements. And this picture, which is actually taken from an article, a recent article here, represents a modern Josephson junction. You can see several details here. So in the center, if you look right in the center of the picture, you will see two metallic electrodes. There's an overlap. There's a little electrode that overlaps with a fatter electrode here. And then the junction is there. It's you see this element is rather tiny. It has basically dimensions of 100 by 100 nanometer. But it is surrounded by a lot of metal. In fact, this is, I have zoomed in on the transmon, which I'm going to talk about a bit later. And this is the tunnel element of the transmon. You see larger electrodes. There are actually, this system is composed of three materials. What you see in the center is made of aluminum. There are two layers of aluminum, which are obtained by shadow mask evaporation. The substrate is sapphire. So this, what you see underneath is sapphire. And then these bigger electrodes, which have a lot of contrast in this ICM pictures, is tantalum. So there are bigger capacitor pads which are made of tantalum. So you see, we can assemble all these elements to form various circuits. And yes?
You don't have this separate, really inductor-like structure, right? The picture you showed does not have a really inductor kind of coil-like structure. No.
Yes, so we have a little bit of inductance in this circuit. So this is a good question. Thank you. So the main inductance is this very little overlap that you see in the center. That's your Josephson element. There is a capacitance of all the metal leads here. So all these metal leads form a capacitor. But you also have a little bit of linear inductance in this kind of wire here. So for instance, this wire adds a little bit inductance to the circuit, but rather very tiny compared with the junction itself.
Is it because there's some kind of twisting structure? Because you cannot make it completely uniform, there's a little bit twisting. Is that the reason why you have inductance? Linear.
Oh, you have, so I have to say that any piece of wire will have an inductance. Any straight piece of wire will have an inductance. In fact, you have 1 nanohenry per millimeter. So if you make any piece of wire, you will have an inductance. You don't need to twist it in a coil. If you twist the wire and make a coil, you increase the inductance, but just the length of metal will give you an inductance.
Michel, the junction is between two layers of aluminum. They're one on top of the other, and you've got an oxide in between. Is that?
Yes. So as you can see, there's a very tiny overlap here.
So this is the sandwich, that thing that you have coming out.
The tantalum, yes, there's a contact between this tantalum layer that you see with the huge contrast and the aluminum, but the surface is so big that you can ignore the junction there. It's like a shot. Yes.
So could you point out the actual Josephson junction here, please? Where is it exactly?
Yes, the junction is let me point it. So the junction is this overlap region here.
So it's a top aluminum, bottom aluminum with an oxide in between.
Yes, there's
The
an
native-
oxide, but
it's a
it's
native-
very, very hard to, you cannot image this oxide on this kind of device. You would have to do, you would have to cut the junction and then do a TM on the interface.
So why do you have two layers of aluminum?
Well, you need two layers because so the aluminum has this wonderful property that after deposition, if you bleed a little bit of oxygen in your chamber, the aluminum will cover itself exactly the right thickness of oxide, essentially one nanometer. And then if you do another evaporation, you see the two evaporations are shifted from each other using a special mask. And then the second layer will overlap the first layer, and that creates the junction.
I'm just confused because on both sides you have two layers. You don't need it, right? You could have had one on one side and one on the other.
Yes, exactly. That's a very good question. Well, you could indeed deposit a first layer and then a second layer, but the problem is that when you're going to do a second lithography step, you're going to damage considerably this very thin oxide layer that you have drawn. So the only way to make a junction is that this first oxide layer has to be pristine, completely pristine when you deposit the second layer. No one has been able to actually go around this constraint. It would be nice if we could make the junction in I would say, a more elaborate way. This, by the way, this recipe that we have been using here is the recipe invented by Java in 1960 for pioneering work on superconductivity. And that's basically the same technique that is used today. No progress whatsoever, and maybe this is something we can discuss in the panel.
I think you've probably just answered my question, but my question was, why these particular materials to build it? And is there any value in thinking about other types of superconductors, or is it?
Well, you know, this is a good question. Can't we use other material? In fact, apart from this tantalum electrode, which was a very recent progress introduced by Nathalie de Leon at Princeton, the fabrication of Josephson junctions have not evolved much. It's not that people haven't tried other things. In fact, there have been many attempts, but when it comes to have the most non-dissipative junction, this original recipe has been found to be the best. In spite of I can assure you that people have worked on this problem for decades, but still this original recipe is, in fact, I can tell you something which is even absolutely amazing. So in this overlap, in the overlap between these two layers of aluminum, you have this aluminum oxide, whose composition is even debated. But this oxide, it is known that it is 10 times better in terms of quality than the best sapphire crystal. You know, this oxide is basically aluminum oxide, and sapphire is also aluminum oxide. Well, the substrate on which this device is made is worse, even though it's we take the purest sapphire crystal. It's worse. It's at least 10 times worse than the junction itself. It is not very well understood why this miracle occurs, you could say that perhaps this oxide is encapsulated between two metallic layers, so maybe it is better protected than the bulk crystal, but this remains pretty much an empirical
It's not
mystery.
even the crystal, right? It's amorphous form, amorphous, right?
So if you believe in transmission microscopy, and not all pictures obtained by electron microscopists are not artifacts, not all of them are artifacts, then it looks like this oxide layer is amorphous. Whether this is true before you treat the junction to observe it with the electron microscope is.
I guess I'll continue the question. So, what makes aluminum good, unique?
Oh, that's a very good question. Yes, why aluminum is unique? Well, aluminum for Josephson junctions for artificial atoms is unique in three different ways. It does. Often it is said that aluminum is the silicon of superconductivity, but in fact you can. It's even. I think it has even dimensions that makes it even better than silicon. So there are three advantages. First of all, the superconductivity itself, the pairing of electrons in aluminum, is really completely follows BCS theory. So you know exactly the kind of pairs you have. It's there's a very large coherence length in aluminum. The pairs are very big, so they average over a lot of impurities. So that's an excellent thing. The transition temperatures is low, but it's only 1 Kelvin, but then that's correlated completely to the size of Cooper pairs. So you benefit a lot from very large Cooper pairs. Laura, who has worked on ITC superconductors, can confirm that it's not so easy to have a superconductor with very short coherence length. So you are happy that the coherence length, or equivalently the diameters of Cooper pairs, is very large in aluminum. So we know we know that the superconductor has a perfect gap. So there's no density of state in the gap in the superconductor. That's very good for dissipation. Then there are two other miracles for aluminum. So it has this native oxide. So if you deposit a layer of aluminum and you just introduce a little bit of oxygen in this chamber, there's this oxide, this native oxide will grow. It will grow with the exact thickness that you want. And it is a very, very good oxide. It has a very good, you can get a conformal coverage of your metal. So that's the second miracle, an oxide which is at least as good as silicon oxide, which is crucial for making CMOS transistors. And then the third miracle is that this metal, aluminum, lies at the midpoint between the soft metals, like lead, indium, or tin, and the refractory metals, like niobium or tantalum. So the soft metals also form good native oxide, but because they have mobile defects, dislocations in particular, upon cycling, you will destroy the oxide. You will actually, the oxide will not be robust to the motion of these defects. And on the other side, if you use refractory metals to make the junction, like if you want to use niobium, this has been tried, tantalum too, but essentially you cannot deposit this kind of shadow techniques, which means that you have to deposit through a stencil. Essentially, you cook your stencil with the heat that you have to generate to evaporate the metal. So, believe me, people are trying to solve all these problems, but so far, at this point in time, the best junctions are still made in this way. But we welcome, any new techniques that will, and we can, maybe with Chris later on, we can discuss the kind of progress we could make in this one. Okay, thank you for this question. So now we discussed the oxide property a lot, so we feel that this oxide is not the main problem, because in fact there are other problems. So even before you worry about the quality of the junction itself, there's a lot of things that you have to solve. And in fact, maybe the reason why there's not a huge motivation, there was not a strong push to improve the junction itself, was perhaps because there were many other trivial problems to address. I think we probably, I'm going to tell you about all these problems, but I think that for the most part, they begin to be under control. So we are living maybe an era now where we can maybe address this question of materials. But even leaving materials aside, you have essentially 5 things that you have to do correctly. So first of all, you have to design the circuit so that you don't have radiation, you don't have dissipation to other electromagnetic modes. So there's a microwave engineering involved, so you need to do this part correctly. You have in superconductors, you have vortices. So for instance, in these big blocks of superconductors, you can have vortices. In fact, it is believed that this C shape is has a good effect in the management of vortices. So if you would have a vortex, let's say in here, it would be confined by this C shape. And it would not move. So vortices, the management of vortices, something that is linked to vortices is that you can have broken Cooper pairs. Normally, at 20 millikelvin, if you have an earth made of aluminum, there would not be any broken Cooper pairs. But in practice, we see that some Cooper pairs are broken. There are some free electrons, and so we have to get rid of them. And one way to get rid of them is precisely using vortices, but not mobile vortices. You want fixed vortices that will gobble up the broken Cooper pairs. And then there is this ominous systems that are called two-level systems, which no one really knows what they are, which lie probably on the substrate near the metal. They create dielectric loss in the circuit. And it's not exactly clear what kind of microscopic entities they are, but you want to there are these two-level systems near the junction capacitance. They are very rare in the oxide itself, but they are in the vicinity of the capacitance of the junction, and then they are also there along the wires of your system. So you want to solve these problems also before you address the quality of the junction.
Sure.
Yeah.
We're technically up to time, but I think we should allow you more time. The question with the community here is how much time we want for coffee and how much time we want for the talk. Should we go for What would you like? 10 minutes, 15 minutes more?
I can just, let's go on in 5 minutes.
10 more minutes, I think is good. 10 more
I
minutes,
think
okay, very good.
We don't need to, I just want to finish giving you an overview on what is really the limitations and what we can do maybe to compensate for them. So there's been a certain number of experiments that have shown some limits on this problem. So something that has improved a lot is this junction quality, and basically, as I said, the quality factor, the intrinsic quality factor of the oxide of the junction is still at a very high level, 20 million. We would be happy to be limited only by the junction. The quasi-particle losses are now reduced to a quality factor which is at least larger than 100 million. So we know how to get rid of the quasi-particle. That has been a great progress in the field. And then these two-level systems, thanks to the work that pioneered by Nathalie Delian at Princeton, we have this better under control. So we have now, we can be quite confident that we can reduce the density of two-level system to give you 10 million. Now, yes.
When you say quasi-particle, you're referring to the broken Cooper pairs, is that?
Yes.
Right? Is it clear the origin of this in BCS, or it's not
So
BCS-like, is it?
We think that the origin of these broken Cooper pairs is twofold. There's parasitic radiation that enters in your box, parasitic, far infrared radiation, radiation above the gap. So you have to be very careful in isolating your circuit from this parasitic radiation. But there is also phonons in your substrate that can break Cooper pairs. And these phonons, we believe, are produced by radioactivity. So you have particles traversing your substrate, and that creates shock waves, and these shock waves actually break Cooper pairs. There's here at UCSB the beautiful work by Ben Mazin, who's making photon detectors with 10,000 pixels. He is able to visualize the tsunami, the phonon tsunami that is created when a single radioactive particle traverses the substrate. It happens with the frequency, which is every minute or so, but all these phonons that are generated for a short instant break Cooper pairs. So if you don't remove these broken Cooper pairs fast enough, your circuit will be invaded by this dissipative source, and so that's a problem. So just for a few minutes, let me show you what these numbers mean if we compare them to atomic physics. So I will just go to this slide. So which tells you a bit where we are if we compare with atoms. So let's take the hydrogen atom with which I started. So actually measuring the intrinsic line width of the hydrogen atom, the line width due to dissipation, to the coupling of the atom to the environment mode, the vacuum, the electromagnetic vacuum, was a rather recent experiment. You see, atomic physics has existed since the end of the beginning of the 19th century, but it was only in 2001 that the intrinsic line width, basically spontaneous emission line width, was measured. So as you can see, we can see that the hydrogen atom has dissipation. It's not dissipation less, but the quality factor is 20 million. Of course, if you would take an atom that is used for atomic clock, now it's 10 to the 18 now, so it's absolutely fantastic, but at least your textbook atom, you see as a quality factor of 20 million. Now, if we take the transmon, you can do the same kind of experiment. Actually, when you reach the finest line width, you have to go to another technique. You have to go to echo. But basically, the quality factor which is reached at the moment, given all these sources of dissipation, is about 10 million. So the performance of our natural atoms is about they are half as good as our textbook atom. So this is the real challenge in the field, is how you can get over this 20 million. So for error correction, if you want error correction to really essentially develop its power, we can live with this 10 million and do interesting experiments that I don't have time to present, which show that quantum error correction is possible. But in order to fully develop it, we need to go above this 10 million. We have to go over this 20 million, maybe by a factor of 2. But so that's where we are. Okay.
Thanks very much. Okay, we have time for questions. Sam.
I think early on you mentioned about cosmic ray and error created by that, and also later on you mentioned about this radiation and then phono tsunami. Are you saying really these things happening from cosmic ray and hitting our brain all the time?
Yes, but we have a very strong error correction. So just to tell you on this point of the effect of radiation on quantum computer, I want to mention that although this is annoying, the number of impacts is sufficiently small that everything is okay, because in superconducting circuit, the computation is going to last no more than a second. A second of computation when the gates are...
What is the origin of those radiations?
So an impact every minute is not a big problem. So we won't have to operate in a mine. But there has been experiments showing that indeed when you go through under mountain, these problems are less.
So we somehow survive our brains somehow.
Yeah, but there's so much correction in comparison with a classical your laptop, which essentially has no error correction at all because it's extremely dissipative. Our brain use only our brain use only 30 watts. Your laptop use 100 watt and is much less powerful than the brain. The brain has to be compared with machine learning machines which use essentially a megawatt to when in the learning phase of this large language model, you use megawatts in these servers. So
Yeah, JP.
So you mentioned the improvement in the quality factor, particularly from Natalie's work. That was for the environmental component, right? So what exactly was the improvement there?
So if you want, so what I think to answer your question, I should perhaps go back to what I said. So the phenomenon of superconductivity itself and the Josephson effect are not the limitation. So the limitation are basically things that are outside superconductivity, like dielectric loss, which is defects in insulating materials. We don't know how to make good capacitances. Basically, that's the bottom line. And there is a more trivial, completely trivial other influences that have been engineered out, like for instance, coupling to spurious modes. The circuit is, for instance, in a box. It is in proximity with other metallic electrodes. You don't want spurious microwave coupling that will dissipate energy. But this is things that are engineerable.
But the tantalum, what role did tantalum play?
Yes. So that's yes. So this is something. Thank you. I have. So why do? So let's go back to this picture, because indeed I have to explain what the tantalum does. So what the tantalum does is that for the other parts of the circuits where the tantalum is, you can get what happens is that you can submit the substrate and the metal to very aggressive cleaning. And so you can, it is believed that at least in all the rest of the circuit, you have somewhat diminished the density of two-level systems. So, but it is maybe
So
more...
It's improved contact with the substrate.
Yes, the contact with the substrate, but also probably the defects that are along the edges, and which can be removed by a much more aggressive processing that this particular method favors. So it's more a question of that this method improves the process than, well, it has nice properties, like for instance, it has also a very good oxide, which probably helps. But it's also chemically quite independent from the aluminum. So when you make this part of the circuit, you can remove some of the dielectric defects.
One last question. Yeah, okay.
You said the quality of the oxide layer is 10 times better than the sapphire substrate. So can't you start off by depositing that oxide layer on the sapphire and get
Yes. People have tried to make, actually, this is something that is a bit mysterious. So in certain conditions, for a certain time, groups are able to make excellent capacitances with this idea. But the process is not very well controlled, and there's in the long term, there seems to be something that is uncontrollable in this kind of ideas. So I don't know. I cannot really answer. This sounds like a very good idea. It has been tried, but you know, this is in science. You don't report your failures, and maybe it's a good thing, because you would. What you understand about your failures might be completely actually misleading. So maybe it's a good service not to report that things do not work.
Okay, let's thank Michel. Should we have a slightly later, 20-minute break? We'll start at 25 minutes to the hour, 25 minutes to